Okay, so time to get going, right? Exactly 1 o'clock. I changed the due date for the homework assignment for chapter 18. Okay, so time to get going, right? Okay, thank you. The homework now is due on Friday. Even though the material is not that complicated, this is an introductory chapter, and we have to be on the same page. This chapter is relatively easy because I'm not going to ask you to solve any problems that require application of Gauss's law. It's kind of, it is easy, but it is relatively abstract method that for introductory class probably not necessary. The difficult part of electricity and magnetism comes in the next chapter, chapter 19. With chapter 19, you really have to spend time in order to start making sense of the future chapters and the electricity and magnetism in general. So pay attention. We're building step by step, and if you skip a single step, the entire ladder falls apart. Here is the schedule for the tutoring room. Tutoring is also available via Zoom. You can always scan the QR code. It is also posted on the door of room 104. I am also available anytime that I am not in class or around campus. You can find me in the office without appointment. And so today, let me summarize where we stand with electrostatics so far. So we started with Coulomb's law that gives the magnitude of the force between two charges Q1 and Q2 separated by distance r. We said that the constant of proportionality K is traditionally expressed as 1 over 4 pi epsilon naught, where epsilon naught is electric permittivity of vacuum, a fixed number, constant of nature, important constant of nature. After that, we defined the first concept, the first abstract concept for the semester, the concept of electric field. Electric field is, at some point in space, is equal to the force that acts on a test charge placed at that point, well, divided by the value of that test charge. Well, keep in mind that very often this definition we're going to use in alternative way, in a way to find the force. So very often you're going to be told the electric field at that spot, at that point in place, in space, is certain value. Find the force that would act on a charge Q placed at that particular spot. And you find it by saying that the force is a product of the electric field times the value of the charge. So you're going to see, once you start doing the homework assignment, you're going to see that very often we're going to think about the electric field as a scene that is set up by some actors, and you place a person at some point, and that person reacts to that field. This is the philosophy that we're going to follow. If you combine the definition of electric field with the Coulomb's law, you discover that the electric field generated by certain charge Q is just given by the value of that charge divided by the distance between the charge and the point at which you want to find the electric field, multiplied by the same constant of proportionality K. It is convenient here to substitute the constant of proportionality K with its equal, so that the electric field is going to be Q divided by 4 pi epsilon naught r squared, the electric field at the distance r from the charge. It is desirable here to use absolute value because this formula gives you the magnitude of the electric field, so negative charges shouldn't bother. You have to get a positive magnitude for the electric field.
So what is represented by epsilon naught?
Epsilon naught is called electric permittivity of vacuum, and it is one of the few constants of nature. And it has numerical value of the order of 10 to the negative 12, 10 to the negative 11 SI units. After that, we spent time to visualize this abstract concept of electric field. So we said, well, electric field attaches an arrow, a vector to every point in space. But since we're lazy, we don't want to draw infinitely many arrows all over the space. We connect the electric field vectors that are in general pointing in the same general directions with the continuous line, which we call electric field line. And after that, we said, well, let's describe the properties of those electric field lines. They originate from plus or from infinity, end up at minus or at infinity. The electric field lines never intersect. And the density of the electric field lines is proportional to the strength, the magnitude of the electric field at certain spots. Another important verbal discussion is related with the properties of metals and electric fields. So we said any excess charge that you place on a piece of metal is immediately going to move to the surface, to the outer surface of the metal, usually outer surface of the metal. So if you charge this Van der Graaf, all this excess charge is going to be on this spherical surface. So this is the first property. The second property is that if there are no currents, electric currents, the electric field inside the volume of the metal is always zero. So this allows you to build Faraday's cage. So if this is a solid piece of metal, maybe with a cavity inside, this cavity, inside the cavity, you have electric field zero. Inside the bulk of the metal, you have electric field zero.
If like electric field lines are like so small and almost infinite, how is it that they aren't able to get through the small squares in that?
So how come that this metal mesh manages to make the electric field inside zero? Well, with the electric field inside is not zero, it is almost zero. It is so small that the electroscope doesn't feel it. And its non-zero value is due to the fact that you have holes. But if you didn't have holes, you wouldn't be able to see how the electric field reacts when it is inside. This is the first thing. Second thing, if the source of electric field was in motion, you are going to see that in that case, the presence of those holes is going to matter. In other words, you won't be able to cancel the electric field inside completely because of the presence of the holes. To cancel the electric field created by a moving charge, you don't need, you shouldn't have any holes in the screening Faraday's cage. So, two properties of metals. All excess charges on the surface of the metal. Electric field, the second property, electric field 0 inside the metal or in the cavity inside the metal volume. And the third property is that electric field lines generated by sources by electric charges anywhere, outside, inside, anywhere. The electric field lines always perpendicular to the surface of the metal. Always perpendicular to the surface. And actually, they end at the surface. They don't penetrate the metal itself because of the property of the second property that I just formulated. And finally, the final section of chapter 18 is Gauss's law, which says that the electric flux through any closed surface, imaginary closed surface. So you just imagine it. That imaginary surface may go through metal, may go through insulator, maybe in the empty space, it doesn't matter. Any shape also, closed surface, usually called Gaussian surface, is the flux through that closed surface is equal to the total electric charge inside that surface divided by the electric permittivity of vacuum. So using Gauss's law, we figured out that the electric field created by a charge uniformly distributed over very large, infinitely large surface. So uniformly charged distributed on the surface. So usually charge distribution density is denoted with the letter sigma. So the total charge on this metal plate divided by the area of this metal plate gives you the surface charge distribution. Assuming that this surface charge distribution is uniform, which it is going to be because the surface is metal, uniformly shaped metal. So we made the argument that the electric field outside this uniformly charged plane is equal to the surface charge density divided by 2 times the electric permittivity of vacuum. Well, we're going to talk about 2 metal surfaces, flat metal surfaces, very large. One of them positively charged, uniformly positively charged. The other one negatively charged with the same magnitude of electric charge. And well, in the space between those 2 flat pieces of metal, charged flat pieces of metal, the space between them, you're going to have double the electric charge, the electric field. One with this magnitude, the other one with the same magnitude but opposite direction. And therefore, the space between two large plates, uniformly charged plates, is going to have electric field, uniform electric field equal to sigma divided by epsilon naught. So this is for two plates. And so this is an application of Gauss's law. We did it last week. But it is important because two metal plates with electric charge on them, opposite electric charge on them, form a device that we call capacitor, and we're going to discuss it in some detail next chapter. Another application of Gauss's law would be to find the electric field generated by uniformly charged sphere. So imagine a sphere like this, right here. You charge it by turning on the generator. What is the electric field created by this spherical charge? At this point, and at this point, and at any point in space. Well, you can, so here is the total charge, let's say, uniformly distributed on this sphere is Q. Let's make it positive, just to be able to draw it. Total charge Q, positive charge Q, excess charge on uniformly distributed on this sphere. You want to find, let's say, the electric field at this spot, at this point. Let's say that that point is located at a distance r from the center of the sphere. That distance, let's say, is larger than the radius of the sphere. How to find the electric field at that spot? Well, first, because of the symmetry of the charge distribution, you can make the argument that that electric field at this point can be only in radial direction. Only, why? Well, if you assume that it is under some angle, you may always ask the question, why this angle, why in this direction, why not in opposite direction? So the radial direction is the only unique direction available, and you can make the argument that this should be the direction of the electric field. If you rotate the charge, nothing changes, and therefore the electric field also has to not to change, and the only way to keep it unchanged after rotations of the charge sphere would be to keep the radial direction. Well, after that, imagine a spherical Gaussian surface. Imaginary spherical Gaussian surface with center at the charge sphere. So concentric Gaussian surface, imaginary, with radius r. So Gauss's law says that the electric flux that goes through this imaginary Gaussian surface has to be equal to the total charge Q that is located inside this imaginary surface. In this case, it is Q divided by epsilon naught. On the other hand, you can calculate the flux, the electric flux phi that goes through this spherical surface, Gaussian spherical surface. How can you calculate it? Well, by using the definition. The flux is equal to the magnitude of the electric field multiplied by the area of this Gaussian sphere multiplied by the cosine of the angle between the normal to the area. But look, here is one piece of that area. The normal to that area is exactly in radial direction. The electric field is also in radial direction. The angle between the normal and the electric field is 0. Cosine of 0 is 1. So just multiply by 1 if you want. But you know that the area of a sphere is 4 pi times radius squared. And now look, Gauss's law says the flux is this. The definition for electric flux says that the flux is this. So those two have to be equal to each other. In other words, 4 pi r squared times the electric field should be the same thing as the total charge Q divided by epsilon naught. And now moving this in denominator in the other side of the equation, you reach the conclusion that the electric field at distance r from the center of your uniformly charged distributed sphere is equal to Q divided by 4 pi epsilon naught r squared. This electric field is exactly the same as the electric field created by a point-like charge located at the center of your sphere. No difference whatsoever. But a result that is useful to remember. Well, you don't need to remember any formula, but you're going to work with those formulas often enough so that you're going to memorize them without trying. Let's see remarks and questions about. So again, I'm not going to give any problems that require you to apply Gauss's law. On the other hand, if you go through those two examples of applications of Gauss's law, you're going to get certain amount of intuition of how the electrostatic phenomena work. Okay, questions? If not, let me do some conceptual questions. Let me show some conceptual questions. And you can think about those questions as a quiz type of questions. And I'm going to post those files. At some point, I'm going to post those files well before the midterm, so you could not to have surprises on any or any example.
Yes, so you're gonna post these slides.
Yes, I'll post them. So you don't need to take a picture of the slide itself. They're going to be posted together with the answers, of course. But still pay attention and use this opportunity to earn some brownie points. So when you see a question like this, you can answer those questions by raising your hand with appropriate number of fingers. For example, if your answer is answer number 3, do this. And for people on Zoom, well, participate maybe. How many people we have today?
I counted 8.
8 people, okay, that's not a bad number. You can participate either by using the chat function, or if you have questions, again, using the chat, you can.
You have a question?
Yes.
When you said you'd post the slides, will that be to WebAssign?
We're only using WebAssign. We're not using Moodle because many questions are taken from most questions actually. Problems, questions, slides are taken from publisher. And the publisher has copyrights, and therefore you get into trouble if you post them on Moodle. This way, WebAssign has license agreement with all large publishers, and we're not going to get into trouble, hopefully. Yeah, copyright laws are weird things, but this is the world that we live in. Okay, so here it is, the first question. So you have metals here, and you have a charge. Yeah, well, a negative electric charge would be a good answer, but it is not the only possible answer. Because look what happens. Metals contain charges that are easy to move. And this metal material, negative charges are going to move here closer to the positive. They are free to do that. And they are attracted, so they are going to move. This means that positive charges are going to be left on the far side of the metal piece. And therefore, well, positive and negative are going to attract. Well, positive and positive are going to repel, but those positives are farther away from the positive, so the repulsive force is going to be smaller. And the result will be, again, a net attractive force. In other words, a better answer would be answer 5. Look, you can see that very easily. Here is metal piece, electrically neutral. Here is your charge, not stick, but some other shaped object. We charge it. So you see that even though it is electrically neutral, it is repelled eventually from some neutralizing it, so it's sparking. Okay, right, this is so you have follow-up questions almost in every slide. What would have happened if instead of metal you have plastic ball? Well, you can see what is going to happen actually very easily. Here is your charged stick. Charge it. See if it is charged. Yeah, it is charged. And here is one. I don't have a good plastic ball in my hands, but okay, so this is ping pong. It is metallized, but forget about the same thing happens. So we're going to talk about this polarization phenomenon in insulators. But it is similar to what happens with metals, even though it is not exactly the same. Okay, let's see. Next question. So here in this slide, you have a multi-step process, and the order matters. So the steps are described on the lower end of the screen. You start with 2 electrically neutral objects, metal pieces. The second step, you approach them with a charged stick and simultaneously you connect them with a metal wire. The next step, you cut the wire, you remove the wire, keeping the charge stick in vicinity. And the last step, you remove the charge stick. What is the electric charge on the two metal balls? What do you say? What would be the best answer? Yeah. Anybody thinks that it is different from configuration number 3? Yeah, of course. So this process, this 4-step process that is shown here, is what we call charging by induction. You didn't touch the two metal spheres, but still you manage to charge them without touching them.
So the blue ball would be negative in the end because those are attractive forces with the positive conductor, right?
Yes.
And then the other positive green ball would just stay the same because it's far enough away from the positive conductor.
That's correct. Yeah. So look what happens. You have this positively charged stick right here. Well, negative charges want to come as close as possible to this positively charged stick. So negatives are going to come here, which means that the green one is going to be left with less negative, therefore it's going to be positive. After that, you cut the wire, you remove the connecting wire, keeping this stick still in vicinity. Well, after you remove the wire, the negative charge stays here, positive charge stays here. And even if you get the stick away, you still have negative here, positive here. So charging by induction, yes.
This says a charged rod. Are we supposed to know that's a positively charged rod? Is that what charged means?
So this is a picture of positively charged
Okay.
stick. Yeah. Well, a similar thing would happen if the stick were negatively charged. Exactly the same story. The charge distribution again would be the opposite. Follow-up question. What will happen if the two spheres now charged, this negative, this positive, are reconnected with wire? No sticks. What will happen? Yeah, they're going to neutralize, and they're going to be neutral at the end. So the excess charges from one are going to move freely through the wire, and at the end you're going to have neutral spherical objects. So pay attention to this one. And let's see. What will you say? So look, it is not a trick question, but it is important question. Coulomb's law describes the force that acts on either of the two charges. The same force acts no matter which charge, what is the magnitude of each charge. Exactly the same force in magnitude. So the correct answer should be, F2 should be again, what? 3 newtons. That's it. The direction of that force is going to be different, right? The first charge feels 3 newtons this way, the other one is going to feel 3 newtons in opposite direction. They are clearly same charges repel. Right? But the magnitude of the force exactly the same. So this is a manifestation of action reaction. Okay, forces. I'm going to skip a few slides because I don't want to go into details that are covered by the homework assignment. And instead, I'm going to leave this question. So remember that the proton is about 2,000 times more massive than the electron. So the same force as you saw from the previous slide, exactly the same force acts on the electron as the force acting on the proton. Exactly the same force in magnitude. Which one is going to accelerate more? The acceleration. Clearly the electron, because force is mass times acceleration. Large mass means small acceleration, because the force is the same. So the next question is related with this one. Where are they going to collide? What do you say? Clearly close to the position of the proton. The proton is barely going to budge. And they're going to collide very close to the proton. The follow-up question, which particle will be moving faster when they collide? Clearly, the electron, yes. By the way, I posted this Brownie point Google Doc. Please use the link that I sent to assign yourself Brownie points. And also don't forget again to fill information about yourself. The section number, standardized tests that you're planning to take, have taken physics exams, any other things that you want to volunteer. So somebody last semester said that his comment was that I can do the splits. So that's perfectly fine. But if you post a comment like this, if you say something like this, we may ask you to do the splits right here in class, right? So be careful what you're volunteering, right? Is the person that posted that here in class today? Come on, confess, we're not going to ask you to do it today. Yeah. Okay, so let's see. So this question here about the forces is practically asking you to apply the so-called principle of superposition. Big words, but it is very simple meaning. So you have a situation like this. So you have a green charge here, positive, 2q. You have a blue charge somewhere here, again positive, 4q. and you have a positive charge, you locate it here. The question is, what is the net force acting on the yellow charge? And look, the force generated due to the interaction of the green and yellow is going to be something this way. So this is one force. The force generated from the interaction of blue and yellow is going to be this way, and it is going to be a little bit larger than F1 in magnitude. The net force you find by adding those two vectors. The best way to add them is to add them using the geometrical rule for addition of vectors. Meaning you take one of the vectors and you draw a representative of that vector starting from the head of the other one. The sum of the two vectors is going to be a vector that connects the tail of the first with the head of the second. So this is the net force F net. Right, this is vector addition again. Don't forget how to do it both geometrically and by components. So what should be the answer here? So keeping in mind that F2 is larger because of the larger value of the blue, it should be clearly other options. Yeah, clearly option number 2 is the best choice. So they say, what would happen if the yellow charge was tripled? If you triple the yellow charge, what would happen in that case? Well, the direction of the result is not going to change. You're going to scale up by a factor of 3, but the direction is still going to be direction given with arrow number 2. So you do double this and you double also this. What would be the result? So you are going to have 2 in denominator, but 2 squared, 4 in denominator. Therefore, the electric field is going to be reduced by a factor of 2. Very good. So now you double in the follow-up question, you double the distance. What do you have to do with the charge to maintain the same electric field? Clearly, you have to quadruple the charge. So you have cancellation of 4 and 4, and the electric field stays unchanged. What do you say? This is another way to ask again for the principle of superposition. But instead of forces in terms of electric fields, look, you have -2 coulombs here. You have -2 coulombs here. And they're asking about the electric field on the line that is perpendicular to the connecting line of the two charges and exactly in the middle, maybe right here somewhere, let's say. At this point, what is the electric field at this point? Look, electric field has to point to enter, electric field lines enter the negative. So the electric field created by this negative is going to be something like this. This is the electric field created by this one. Similarly, the electric field created by the top charge is going to be the same magnitude because the distance is the same, but pointing in direction to that one. So the net, the total electric field is going to be the vector sum of those two vectors. And you add vectors again using the same procedure. Take a representative of this, draw it here. The result is a vector like this. This is the net electric field E, right here. So this is electric field E. So in other words, if you think in terms of components, the y components of vector E1 and E2 cancel out, and the x components add up, and you get a net field completely in this case, negative x direction. Okay, or not quite? So the answer should be something like answer number 3, right? Vector number 3 should be. Oh, we're running out of time. And you know what? I have one more question left. Let's see this one. What is the electric field created at the center of this square? So it is exactly the same story, but it would be useful to rearrange your thinking. So you have equal negative charges at each vertex of the square. You're asked to figure out what is the electric field exactly in the middle. And look, electric field created by this one is going to be this way. The electric field created by the opposite direction charge here in the opposite vertex is exactly this way. They cancel out. Similarly, electric field created by this one this way, and this one created by this charge is this way. Again, they cancel out. The net electric field is 0, as it should be. And the last one is, well, here you have to calculate it. I'll post this slides.
You go over number 13, it kind of deals with the exact concept. It's kind of confusing because it's different.
Okay, I'll do number 13, but we're out of time, so you're free to go. And we can do number 13 if you're free to stay after class. So I'll post again those slides, maybe a week or so before the first midterm, which is going to be sometime in, I guess, mid-February or second half of February. Okay, let's put it here.